In today's webinar, I will be sharing findings with respect to the recent depth-based PFR study that we did, and also take you through the different elements we considered while methodically carrying out our research. As you all would know, so the offshore industry, the scenario is pretty complex and has several inherent challenges. Therefore, in the pre-feasibility analysis, we tried to break this problem/puzzle into 6 broad categories of stages. In stage 1, we summarized the existing wind resource reports out there in the public domain. Stage 2, we selected potential wind farm zones for future development. In stage 3, we discussed broad techniques of designing a wind farm. Stage 4, high-level analysis of project costing. In stage 5, discussed briefly on the financing options available in the market these days. And in stage 6, we quickly run over some environmental and social impact issues. So for stage 1, which is summary of wind resource reports, at the outset of this project, we decided to gather all the existing credible secondary literature to assess the wind profile existing in the regions of the coast of Tamil Nadu. Some of the notable studies that were considered have been listed in this slide. You will notice that all these slides, especially read by UNEP, INCOIS, and WISO, which are the international studies, are sort of consistent in their wind reading, but the hub height at which these wind readings are measured on wind mass are different. They are varying. Similarly, for some domestic studies that were done by WISE or CSTEP, you will notice that the hub height too is varying. In the WISE 2012 report, where they took BAW's true power data set, you have a hub height of 80. And the similar partner, when he did another study with ORDOM services, they had a different reading of 6.6 meters per second at a hub height of 20. So these studies helped us in a way find average readings of 7 to 9 meters per second at 50 meters height for Rameswaram, and 9 to 12 meters per second at 120 meters height for Kanyakumari. And why is wind resource is important is because even a minor variation of say 10% in the wind readings results in 30% of error in energy calculations. And some prominent gaps that we found in these studies were that they all use satellite data, which is highly uncertain because it is of poor resolution. Measured data were available at low heights, some at even 20 meters, and realistically, turbines are placed at 100 or 120 meters these days, so that's inaccurate information. Studies do not consider spatial constraints that can obstruct offshore development. And in general, all these studies lack adequate spatial and temporal resolution that are required for planning activities. Stage 2, that is selecting potential wind farm zone. Now, so since we were working for the state of Tamil Nadu, and we had to locate the appropriate regions for potential development, we decided to first define our territory. And there will be 3 factors that governed our decision to fix on a territorial boundary. One of them was the exclusive economic zone of our country. The second was the maximum water depth that we could go and explore. So DNV GLS, our technical partners, had bathymetry data sets of up to 500 meters. So they suggested that we could explore this extent of this region for depth for different foundations. And the state maritime boundary of about 100 kilometers along the coastline too was considered. So in this map, if you see the white region just under Tamil Nadu, and similarly, WISE connects the study in Gujarat to the white region of Gujarat. 360 zones. Next, after we defined the territory, the methodology that we adopted for identifying our zones So if you see, we have the territory, but we realize that there were several constraints that hindered this development. So we have to map all these hard constraints and then remove them. So in layman's language, say no-go zone. So something like military practice areas were an absolute no-no and could not be considered for development. So we listed down those constraints. Then second, we had some exclusion. Maybe these are all technical terms, but the exclusion constraints for, say, for example, sediment thicknesses or cyclones, etc., were evaluated for their impact. After this, after evaluating their impact, all these constraints were scored on a score line of from 0 to 10. They were assigned weights. And then this analysis at the end generated the best zones out of the entire region. So few of the hard constraints that we had analyzed, because to allow preliminary selection of zones, a number of hard constraints are needed. These consisted of technological barriers and spatial conflicts which restrict area for offshore development. Some of them were coastline and sensitive mainland islands, pipeline subsea cables, maritime traffic, earthquake zones, cyclone zones around the desired territory, visual impacts from the shore, oil and gas fields, etc. So broadly, going over each one of these, in the state of Tamil Nadu, which has a coastline of 1,076 kilometers, we found that there are these sensitive protected areas, islands around the Gulf of Mannar. These were eliminated. We procured bathymetry charts. DMEGL procured bathymetry charts from the British Oceanographic Data Center and used the TEPCO set of 1 minute arcs, granularity. So these were eliminated. Then earthquake zones, which are found to be moderate, low to moderate in Tamil Nadu, were procured. So this is the IMD data set, and no area therefore that was excluded from study because these were low to moderate. Cyclone zones too were studied from the IMD database from 1877 to 2005. And it was observed that the intensity of cyclones is high on the east coast of Tamil Nadu, but again, those zones were excluded from cyclone zoning. 2 oil and gas fields were found to exist off the coast of Tamil Nadu. PY3 is an oil field spanning over 81 square kilometers and 80 kilometers south of Pondicherry were excluded. And PY1 gas field which spanned over 75 square kilometers and 30 kilometers north of PY3, which is the oil field, 2 were excluded. And similarly, we found some subsea cables and pipelines that ran through the entire belt, through the Bay of Bengal and Arabian Sea. These tracts too were excluded. Some environmental considerations too were looked at. So the Gulf of Mannar, as you can see in this map, spans right from Rameshwaram over to Tuticorin, and this is an extremely important nature reserve. It has 5 bird sanctuaries, 2 national parks, 1 wildlife sanctuary, etc. So this is, as you can see, this is heavily. So it's an extremely important territory to preserve, and therefore the entire region was excluded as a hard constraint. Some minor constraints that we saw that we needed to evaluate were maritime traffic. So we pinpointed all the major and minor ports on the coast of Tamil Nadu so that potential logistics and staging activities for vessels could be evaluated. Sediment thickness, we took the National Oceanographic Association map which measured thickness. But this too wasn't really a major concern, but we still noted this down for foundation considerations for the piles that will be built, so this will have an impact there. Visual impacts and military activities, these are again smaller concerns, but were still necessary to look at. So apart from the hard constraints, there were certain exclusion zones slash constraints which are removed, and they were removed to this extent. So in this table, we've listed down all these features that some of them I've discussed before. And so some say, for instance, the water depth of the between less than 5 meters is considered economically unviable. Greater than 500 meters was impossible because we would not have the technology. Similarly, setback zones, the buffer areas were excluded for coral reefs, mangroves, bioreserves. A region of up to 10 kilometers from these zones was excluded from development. Visual impact, we set a limit of 8 kilometers. Oil and gas, well, submarine communication cables, all were at half a nautical mile. So after we had, so in this entire process of weighting or assigning weights to all these constraints, that was step 1. Step 2 was to help DNVGL compile all the numerous GIS layers and run the simulation models to finally generate the best suitable zones. So while the DNV conducted this analysis, they assigned weights, and as you can see that in the weightage methodology, they gave the maximum importance to wind resource at 40%. So a higher wind resource is always a positive. Second highest weighted score was given to development complexity factors such as water depth, proximity to the nearest port, or distance to the nearest transmission grid or substation, versus lower factors of source environment, because they do not really cause massive hindrance to offshore development. So DNVGL then generated heat maps of all these parameters. One such example is the heat map that we created for the wind speed map. So this is an example of a wind speed map at 120 meters height. And on the right side is a heat map, and you can see that the regions in green receive considerably decent wind portfolio or profile, have a decent wind profile, versus some of those in the red region, or less than 3 meters per second. So finally, this is the map that shows the zone breakup, and we prioritized, stratified these zones from A to H, and A, B seem to be the most suitable zone, with an indicated mean wind speed at 8.2 meters per second, which is extremely lucrative. The mean depth at these regions broadly is at about 20 to 30 meters, which is suitable for erecting a monopile, which I will get to at a later stage. Minimal distance to the nearest substation. So if you notice, all these factors play an important role in terms of financing these projects. Distances, supports, logistics activities are a major chunk. So the best possible suitable zones after integrating all those constraints gave us the tentative zone. Just to share with you a high-level assessment of these zones, so I won't go into detail for each one of those. But say for each one of those, we highlighted the concerns in the remarks column. So say if you take zone B, it said that it has low sediment thickness, and hence a detailed subsea geology study is required for determining appropriate foundation choices for wind turbines. Then it's a near Kudankulam nuclear power plant, so presence of the jetty is close to a zone which could be used for staging activities for wind turbine vessels, etc. So we've obviously listed these remarks for all these zones. Now, after we've defined the zones, we've defined and highlighted all the tentative zones. It was necessary to then delve deeper into the preliminary wind farm designing concepts. So this section of the webinar discusses design considerations for a typical commercial scale offshore wind project. Also elaborates further on some technical consideration and potential risks at zone level. So wind turbine characteristics, we realize that for a profitable offshore venture, the ideal capacities to look at would be a 4 megawatt or 6 megawatt wind turbine generator. And wind turbine generators are designed typically are very site specific and are designed after assessing the climatic conditions or the general climate profile in that region. Foundation, the two categories considered for this analysis were monopile and jacket foundation based on European projects, because those learnings in those projects helped us understand the implications of working in different depths. So this study, though, was limited to an extent of 70 meters, up to 70 meters into the water, because greater than 70 meters is perceived to be not economically viable at this stage. Similarly, while designing a wind farm, we'll consider factors such as the installation constraints in general and operation and maintenance parameters. The wind turbine characteristics of it, basically wind turbines are classified into 4 types, they are called wind turbine classes. The International Electrotechnical Commission, IEC, specifies standards for wind turbine design that are used in Europe to certify turbines and related electrical infrastructure. The Commission also defines wind turbine classes that cover most conditions in which turbines would be erected in the future. So it is now since it's possible that due to cyclonic conditions of the coast of Tamil Nadu at a particular location, the area may not be fit into any of these set classes of 1, 2, and 3, and so therefore a 4th class exists, which is the special or the F class, which caters to turbines have to be customized to location-specific needs. Moving on, to the wind turbine foundation screening study. The foundation typically depends on site-specific conditions of the condition of soil, water depth, core or erosion potential at the site, turbine capacity, cost, and environmental loading conditions, because even though it's understood that offshore wind turbine industry can learn from the oil and gas industry, but with respect to the offshore industry, they have a lot more movement happening with vessels coming at more regular intervals for maintenance and logistics reasons. So the loading conditions and unloading conditions are very different as compared to the oil and gas industry. Some standards pertaining to foundation are ISO 19900 to 19903. But if you have any doubts regarding these, you could probably get back to me at a later stage. Now, going to the next concept, which is the electrical infrastructure study. We might need to research this domain a little further, because the current grid infrastructure in the state is not equipped to handle additional burden of the offshore industry. And so additional transformers, substations, and grid lines will have to be installed at a later stage. Even additional facilities like putting offshore helipads and communication systems will be needed. So these are the current inadequacies in the system. Now the existing port infrastructure seems to be inadequate for offshore development, and additional retrofitting for wind farms, installation, and offshore and maintenance operations is recommended for ports. And you need special vessels, which are wind turbine installation vessels and jack-up barges, to perform these activities, which are currently unavailable. So maybe spare vessels which are used currently, again, by the oil and gas industry, could be retrofitted for these purposes. And while conducting installation, there are risks of transporting goods in harsh conditions. So therefore, there is a need to schedule these activities at the right time, and also have the right, the right insurance policies, because these are absolutely unpredictable risks that developers can be subjected to. Water depth affects the foundation and assembly method. Now, the assembly method is of various types depending on the depth at the site. So either they could be drilled and then grouted to the floor, or if the soil is too loose, then they will have to use suction techniques. So they're pretty complex methods, which we intend to research a little more on in the later reports. Now, installation has to be planned around the cyclonic conditions because they do pose serious threat. Moving to operation and maintenance considerations, there can be two strategies that can be adopted. One is a simple workboat strategy, and the other one can be a workboat plus helicopter strategy for farms that are further away. So the first strategy, which is the workboat strategy, is relatively inexpensive. It can carry large number of technicians, useful for short distances. Response time and accessibility depend on transit time and CSTEP, but are generally comparatively less, and are used for scheduled O&M activities. Whereas sometimes versus the second strategy, which uses the helicopter, it is expensive, carries few technicians, takes longer. It's useful for longer distances. There are short response times, and used for unscheduled O&M activities in case of emergencies and sudden requirements. Key technical risk consideration. Now, with every factor there is a certain risk involved, and therefore, hence the complexity of this industry, the case. So, if for instance in resource measurement, you need accurate resource measurement. Turbine technology, you need to choose the right wind turbine to get the optimal cost of energy at the end of the day, because you cannot have a big turbine and less wind at a location. Then foundation, they vary different on-site conditions. Subsea cables, now these are dug deep into the seabed, so damage to subsea cables during installation procedures has human-induced hazards while anchoring in natural hazards such as seabed. Construction, additional cost due to delay in scheduled activities is possible. There are high health and safety risks involved. Grid availability. There's unavailability of grid which needs to be covered up for. There's weather risk, and then there is at the end availability of marine logistics. So after having gone through the designing concepts, we move on to the high-level preliminary project costing of offshore wind projects in India. So DNVGL helped us, generate levelized cost of energy numbers, but the DNVGL cost model was designed to model commercial scale European projects, and hence contains information and modeling capabilities of that scale. The levelized cost of energy, though, was calculated for each zone with a resolution of 2 kilometer data, so which is not bad for a pre-feasibility study. Certain dimensions were set into this model. So we set the turbine capacity of 4 and 6 megawatts. We set a farm capacity of 150 megawatts and 504 megawatts, because that is considered a reasonable scale to kickstart a pilot project or first project. So farm capacity, turbine capacity, and foundation type. Just those two, the turbine capacity and farm capacity, and the model by itself, after running simulations, optimized these readings, and then generated the suitable foundation types and the electrical infrastructure required, which is the cabling. So it generated which zone requires which kind of foundation, at what depth, at what connectivity, whether a 132 kV line or a 110 kV line, etc. Now, after we had levelized cost of energy, it was necessary to evaluate the general components of capital expenditure, Capex, capital expenditure, operational expenditure, OPEX, and energy production. What would be the individual components of these three cost items? So turbine costs, foundation costs, electrical costs that includes the intra-array infrastructure, offshore substation, export transmission infrastructure, etc. Consisted of Capex, whereas OPEX included operations and maintenance activities and a nominal 0.3% of auxiliary electricity usage from another captive source. But we have to bear in mind that these assumptions are UK cost estimates, including material or labor costs. The entire zone poses the same water depth. We didn't have, this model didn't account for varying water depths and wind climatic conditions. Then wind availability and zonal climate conditions are based on publicly available information. This wasn't valid site-specific information, for instance, that could have been collected from a LiDAR equipment or a accurate met mass. The fourth is that the cost of energy assets for water depth is only within 5 to 70 meters. We could have explored further deeper territories. So this model was run for two capacities, as I mentioned, 4 and 6, for two wind farm capacities. But we are now considering the maximum capacity, which is 504 megawatts with a 6 megawatt capacity turbine. So for the likely zones of A, B, C, and D, which are the tentative zones, we find that levelized cost of energy is lowest for A at 13.13 rupees per kilowatt hour, 14.28 for B, and so on. And you'll notice that this model therefore has generated which export infrastructure is suitable at what depth for which zone, so, and at what annual energy production. So after running this analysis, we generated a map that lists down all these zones, and you can see that in this map, zones A, B, C, D, the green are the more likely zones to be considered for development versus FX, G, and infrared. So their complexity is increased further analyzed in a detailed feasibility report. The financing options available today to developers in stage 5 that we'll discuss are, say in India, debt financing or taking foreign currency loans. Support on supply chain, if your vendors or sometimes vendors fund other supply chain members lower down in the chain to build capacity, or refinancing short-term loans, taking loans on equity, mezzanine financing, etc. The new convention in Europe that is seen is that they take direct balance sheet financing. But again, we will not delve too much on this. Probably take it up in the next webinar. Now, tariffs from existing RE sources, renewable energy sources that we see. So onshore wind currently costs 3.5 rupees a kilowatt hour, versus we earlier saw that for zoning the costing is at 13 rupees, so roughly 4 times the cost. Similarly, solar is 7 rupees, biomass is 4 rupees. So if offshore wind tomorrow has to catch up, it drastically needs some incentives from the state and national government. So some of the incentives that could be considered are the already existing incentives, such as generation-based incentives, import duty excise, accelerated depreciation, soft loans from ARIDA, etc. All these mechanisms could be used to give impetus to the offshore industry. Lastly, the environmental and social impacts that the offshore industry faces. We predict that there will be a change in migratory path of birds. So these need to be studied. There can be an impact that could be felt by the fishes in the belt. So detailed analysis requires with respect to sensitive and commercially important species, because if there are certain commercially important species in certain locations, those will need to be analyzed for development. There's an effect of electromagnetic force and thermal radiation from cables that needs to be studied on fishes. This is all with respect to Tamil Nadu. We had done a broad study of all, we had analyzed case studies of all the offshore wind projects in the world, and therefore have learnings that we have now implemented in this case with respect to Tamil Nadu. There's no environment, so now the high level analysis of social impact. So we perceive that offshore wind technology will be widely accepted because it is a cleaner source of power. There are no environmentally harmful gases. It's estimated that 100 megawatts of wind power project will reduce 3 million tons. 3 million tons of carbon dioxide annually. So in general, this sector will generate employment. It's labor intensive as compared to fossil fuel technologies. It will lead to generation of new jobs, roughly 21,000 jobs per year, every $1 billion invested. Summary of preliminary findings. The summary that can be broken down into 3 categories: spatial, technological, and financial. Some spatial conclusions are that most economic zones are A and B. Reasonable conditions for development are found in C, D, and F. But in zone F, we find that it's a comparatively low complex zone, and the water depth is low, so it's easy to put a drill foundation versus a floating foundation, which is expensive. Shorter distances to a substation, so again, low cost on grid connection per se. So these are some of the advantages. Technological findings are that the most suitable wind turbine that we feel will be suitable for the wind profile will be a 6 megawatt turbine. Suitable foundation structures such as monocar and jackets will be suitable. There's inadequate infrastructure currently for operation and maintenance activities, but in the recent years, as it's developed, will give a positive case to offshore industry. The financial findings are that the cost of energy ranges between 13 rupees to 16 rupees per kilowatt hour, which I mentioned is 4 to 5 times that of onshore wind energy. So require subsidies similar to wind and solar to catch up. Recommendations are firstly that a detailed LiDAR campaign should be carried out to validate existing secondary data. We need authentic cost of energy estimates based on detailed local infrastructure studies, which broadly are discussed upon the components of Capex and Opex. Detailed studies that need to be done as far as site-specific analysis is concerned. For a deeper feasibility report are bathymetric, cyclonic conditions, environment and social impact assessment. Those are the broad recommendations. And so now our roadmap for the second year is to complete the detailed supply chain, grid infrastructure and logistics study, and also then conduct a LiDAR assessment campaign. So the picture as of now is very blurry, but we will soon find the answer. Thank you for listening.